And now let's take a look at 2.08 absolute value functions. Our goals are short and sweet. Describe the effect a given parameter has on a graph, and graph an absolute value function given its equation. And we will also be seeing if you can come up with the equation given the graph. So to start us off, what do you think an absolute value function has in it? An absolute value sign, of course. Now keep that in mind. And remember, absolute value signs are these two straight vertical lines with something in the middle, which represents the distance away from zero. So keep that in mind and think about what the vertex form of a quadratic looks like. We've done this recently, so you should know that it looks like this, with all possible transformations. Athletic A, dishonest H, and elevator V. Okay, we're going to put those two things together. I'm going to tell you right now that an absolute value function with all possible transformations is almost exactly the same as this vertex form of a quadratic. There's just one thing that's different. You know what it is? Well, didn't we just say these have absolute value signs? So the only difference is we are replacing the parentheses with absolute value signs. That is the parent function of an absolute value function with all possible transformations. Now, we're going to look at a graph right now of the parent function. If you take a look right here, you'll see it's simply written as f of x equals absolute value of x. That's the function written out. We're not looking at all the possible transformations. We're just looking at the basic parent function. So what do you notice and what do you wonder? Hopefully you notice there's a vertex. It is a V-shaped line. It almost looks like two lines, doesn't it, with a corner. And it goes up in both directions. So one very key piece of information to know is the vertex of a parent function is at the origin. Now, other than that, let's think about this parent function. My question for you is there any number we can put in for x that gives us a negative value out? No, right? Because absolute value is distance from zero, right? So if we put in, let me get my highlighter. If we put in negative x values into our function, we are only going to get positive y values out, which is why you see this line going up and to the left. But it's absolute value, right? So you can also put in positive x values. And again, you'll get those same positive outcomes. So this line also goes up and to the right. Notice also the slope. The slope is 1, right? Rise over run. We go up 1. Let me get a different color here. We go up 1, right 1. Up 1, right 1. And that happens as well on the left, right? Because just like a parabola, these functions have the same thing happening on both sides, meaning there is also an axis of symmetry. There is that reflection effect going on. Here are our good friends once again, came to join the party. You've already seen the parent function with all possible transformations, and you should be no stranger to all of these transformations. If it's negative, you flip it. You might want to think of it as a sad face. Sad for negative. If that's a parabola, upside down, same thing if it's an absolute value graph. Athletic A affects the vertical stretch and compression. And then, of course, the sinus H and elevator V, which are those shifts, horizontal or vertical, meaning left, right, up, and down. Now we're going to use these two first when we're graphing these to plot that vertex. So remember I said that's your guiding light. That's like your anchor. Okay, so keep that in mind as we look at what is happening here. We just looked at all of the possible transformations. We know there's some things happening here, but can you identify exactly what those things are and why? Now that you've had a moment, let's look together. The red line here you can see is the parent function because the function looks exactly the same as what we just pointed out. So parent function on both is the red line. But different things happening to the blue line. That is the transformed line, right? So what's happening over here? Well, all of the points, all of the y values, I should say, are getting pushed down. They are getting smaller. So what kind of change is that? And then over here, what's happening? Well, all of the y values are getting greater. This blue line is moving up, right? So you've seen this for different types of functions, but we're seeing it again. Hopefully you notice if there's an upwards or downwards movement, that is a vertical movement. And here we're going to say there was a vertical compression. Things are flattening out, okay? If it's flattening, it's compressing. And when does that happen? Or why does that happen? And it's all about A, right? Athletic A. That value, let me get a highlighter so you can still read it. This value, let's try that one more time. This value out front, athletic A. Okay, so when is there a vertical compression? It's when you have A being what? Well, it's obviously less than 1, right? But is that it? Like, can we have A be -2 and there's a compression? No, because remember, negative just means you flip that graph upside down. That does not affect the stretch and compression. So what we need to say is specifically when A is between 0 and 1, so it's a fraction or a decimal that's smaller than 1, that's when that vertical compression happens. And then on the right, we see a vertical stretch when what? Well, we see A here, right? When A is greater than 1. Those are our vertical stretches and compressions. Okay, notice 1/4 on the left, 4 here. And if you think about it logically, it really makes sense, right? Because when you plug in x values, you're solving for g of x, which is also y. Well, that must mean all of these values are getting multiplied times 1/4. They're getting cut in a quarter. They're getting much smaller. So that's why these y values are dropping down, resulting in this very shallow v. Okay? Over here, you're multiplying everything times 4. So the y values are increasing quite a bit. Now, if you're thinking, well, I don't know, this kind of looks like this blue line went to the left, it went inward, and you're right. Visually, that looks like it did. But what's actually happening? Well, what's happening in these functions is we're inputting the same exact x values. It's just the y values, the outputs that are changing. Okay? So this x value of 1 resulted in a y value of 1. But for this function, when you put in 1, it results in a y value of 4, right? Because 1 times 4 is 4. Now we've recapped all of the transformations. It's a great time for you to try to see if you can graph all three of these. And now let's do it together. For any graph, remember I said the vertex is your guiding light, right? So I'm going to draw that vertex point at every origin, just to remind myself. If I look at the function here, I see you always want to start with h and v with these graphs. So h, dishonest h, means move right 4. So let's take that dot and let's move it right 4. So now we're here. And elevator v means down 3. So down 3. That's going to be our new vertex. Are there any other transformations happening in this function? No. So, simple as that. We graph our slope up to the right. Let me make it a little more accurate. We want a slope of 1, and we want the mirror effect on the left. Technically, that goes up for a while. I'll stop it right there. Goes up forever, right? Graph number 2. Where does this dot go? Dishonest H, opposite direction. We're going to move left 3, and then we're going to move down 1. There's our new vertex. It is negative though. That's the only other transformation. So we want flip that upside down. And that's it. No stretches or compressions. Now, graph 3 is going to be a little different because we do have athletic A here wanting to stretch our graph. So dishonest H takes us right to elevator V, moves us up to, we have our vertex, and there's a positive 3 out front. Now, if you're not familiar with where to plot a point based off what we've talked about, you can always plug in x values and discover what other points are. But I'm telling you right now, if it's 3, that means there was a slope of 3 over 1. So instead of rise 1, run 1, we go rise 3, run 1 point. And then we know there's that axis of symmetry, and my point disappeared. There we go. So we also have a point over here. Connect the dots, and it's happy days. Time for another question. This is about the vertex. Specifically, what do we do? What happens if x is all alone in that absolute value sign? Well, your vertex is HV, just like with quadratics, right? Especially if it's in vertex form. So, what's H? We do not see anything with X. It is all alone. That means there is no horizontal shift. We are not moving left and right. We're only moving down 2, so that's where our vertex will be. I guess this might be a little confusing with the two V's, so I'm going to write out a vertex. But can you write the function by looking at the graph? Test yourself. We know we can name a function f of x, g of x, something like that. We know we're going to have an absolute value sign because we see that v and it will be squared. But what else is happening? Well, test yourself, pause this, and then check it. Upside down, so obviously negative. X inside, always. What is H and what is V? Well, looks like I might want to label my graph a little bit because it looks like every time I go over two squares, we're going up by 1. So that's always something to be very careful with on graphs. Okay, so in this case, what's happening? Well, we started at the origin, we went right 4. So right 4, that means dishonest H minus 4. And then we went up. Up how much? 5. Or wait, where did I get 5 from? That should be 3. Whoops. Let's make that a 3. And here we go. Plus 3. Now, what about A? Can't forget about athletic A. Let's take a look back at our graph. We know the parent function goes rise over run, 1 over 1. So this would have been if we had a negative parent function, but that's not what we have, is it? So what we need to really do now is identify two key points to really determine what that slope is. Well, I see a clear point there at 4, 3. And where else is a clear point? This is 4.5. I'd rather not do halves. 5, 1. There we go. 5, 1. So, how far did we go? Rise of 3 to 1. That's 2. Down 2. And then run 4 to 5. That's 1. We don't need to worry about the positive or negative because remember, that just determines if it's flipped or not. So now we put A as 2, and there is our function. And I have one more question for you today as an exit ticket. Explain how the graph of g of x, that function you see there, would compare to the graph of f of x. Hopefully you notice there are two things happening. So for the graph of g of x, it would be flipped upside down because of the negative sign and vertically compressed because a is between 0 and 1. We can clearly see it's 1/2. And that's all I got for you today.